All right, first of all, great to see my CENTRIC colleagues again, and also happy to see the external audience for this at this webinar here. So for this presentation, I will talk about the downlink control information compression. So this is a work jointly together work with my colleagues Alvaro, Pavan, Zheyang, and Homa. So for this downlink control information compression, as its name suggested, it's about a lossless compression technique for the downlink control information to improve the reliability of PDCCH. So let's see the agenda of this presentation. I mean, it's quite straightforward. So there will be three main parts. First, I'll talk about the technical problem, about what research problem we are trying to solve here. And then I'll briefly describe about the transformer-based DCI compression technique we propose. And then lastly, there's one RC signaling part that I'll present here about the DCI compression. Because DCI lossless compression is a technique to compress the DCI message in order to make it practical to be used in standards. There are some signalings we need to introduce to the PDCCH scheme. So that's why I've also put one slide here about the RC signaling. So first of all, about the technical problem we're trying to solve here. As you may already know, it's about DCI compression, but why we need to compress this DCI message is simply because there, in our wireless system, we might easily encounter this control capacity bottleneck, which means if there are many UEs in the network, and we need some frequency resources to control these user equipments, right? But if the number of resources is limited, we might not be able to control that many UEs in a limited time. So a direct way to solve this problem is to reduce the length of the DCI message, because the shorter the length, the less number of resources will require to control one UE. So that's why here we try to work on a lossless compression technique to compress this DCI message so that we can control more UEs in a limited time. And talking about lossless compression techniques, there are usually two main types of compression techniques. So one is lossless and the other is lossy compression. And there are many lossy compression techniques proposed by many researchers and engineers. But those techniques are not ideal for PDCCH in a wireless system because it's a control channel. We don't want to introduce any errors to the control bits in this PDCCH. So that's why we choose these lossless compression techniques to losslessly compress the DCI message without introducing any errors to the control bits. And for the conventional approach, there might be Huffman coding. That is a dictionary-based method where we collect the frequency of each symbol, generate one table or one dictionary for the symbol to be compressed. And then based on the frequency, we generate the encoded bits for the symbol. And then in the end, we concatenate those encoded bits into one encoded sequence. And that will be the losslessly compressed sequence. And the problem for that is it's not optimal because sometimes the underlying correlation between these symbols are not that easy to be collected just based on one dictionary, right? So people propose this deep learning approach to use a neural network predictor to estimate the probability distribution of the symbol to be compressed. So in that way, the neural network will return one probability distribution estimate as an input for the arithmetic encoding. And then these arithmetic encoding will return the encoded bits, and it follows one sequential manner. So you start from the very first symbol to be compressed. Then the neural network predictor will estimate the symbol, the probability distribution of that symbol. And then the arithmetic encoding will return the encoded bits, and so on until the very last symbol. So this deep learning, this neural network serves as one neural network probability distribution estimator. The more accurate of these estimate, the shorter of the length that the DCI message can be compressed into. So in our work, we propose a transformer-based architecture for these DCI compression, where the transformer model serves as the neural network predictor to estimate the probability distribution for that symbol to be compressed. So there are two types of features we try to let these transformer to explore or to learn from. The first one, we call that time domain features, where the past DCI messages will be served as the input for the transformer model. So because, as we may know, these DCI messages might be highly correlated in a real wireless system, from the past TTIs to the current TTI for the DCI message to be transmitted. So by exploring these time domain features, this transformer model is expected to learn the correlation between these DCI messages in the time domain. And the second type of features correlation we try to let the transformer learn is from, we call this spatial domain, where the each field in one DCI message might be, those fields might be correlated, like the power control comment or the frequency domain scheduling comments. These fields might also be correlated, and we also need to explore these correlations so that the neural network based or the transformer architecture here can perfectly learn these correlations and give an accurate estimate on the probability distribution. And again, like the previous slide showed, the architecture where these probability distribution estimate will be serve as the input for the arithmetic encoder, and then we encode from the very first symbol to the last one. So in the end, we'll have one encoded sequence to be transmitted in the PDCCH. Okay, so one example about these result of these transformer-based and Huffman coding, and then also this slide shows our motivation again about why we want to compress these DCI message. So on the top of this slide here, we can see this is our original DCI message, where the white dot refers to a bit of 0, and then the light blue refers to the control bit of 1. And the star blue refers to the node space. The more number of these node space, the better of these compression ratio has achieved. So we can see conventional method can also achieve a fairly well performance on this compression, but compared to the transformer base, it's not that good. I mean, the higher the compression ratio, the better that we expect to achieve for the reliability of these PDCCH. And here I also illustrate by the idea that the shorter of the length of the compressed DCI message, the less number of resources will require to transmit these DCI message, and then the receiver side, these under different scenarios, they can achieve the same block error rate, so that we just need less number of resources to get the same target block error rate. So that's in the very end, we can control more user equipments in a limited time. So this again highlights our motivation of this DCI compression work. So during the research work, we investigated some training techniques to further improve the compression ratio of these transformer-based architecture. So this slide shows two training techniques we investigated. One is about the field reordering, because talking about machine learning model training, usually one common problem we might encounter is about this overfitting. So one training technique we found is to interleave this field order based on the entropy value. So instead of just using the default order of the fields within one DCI message, we can estimate the entropy values and then reorder the field, so that during the training phase of this transformer model, it will not be that easily fall into the overfitting case. So it can improve the general performance of this trained model. And then the second training technique is the buffer delay length selection. So just now in previous slides, I showed that we want to explore the temporal correlations, and there might be one memory buffer to be used to store all the past DCIs. But one question is, are those latest DCI messages the past DCI message have the strongest correlation to the current TTI? And the answer might be no. So we can estimate the importance metric for each delay length index and then select those delay index that have the strongest correlation to the current TTI. So based on this delay length selection, it can further improve the compression performance from these deep learning based methods. So yeah, these are just some training techniques we found that are useful and easy to be implemented for these DCI compression work. So some numerical results about these DCI compression. So the first one, these slides show some numerical results from MATLAB system level simulator, where we use MATLAB to generate some scheduling logs. And then based on these scheduling logs, we create DCI messages. So we can see on the top here again, we have the original DCI messages where you can see it's correlated, right? You can see the pattern here, they are strongly correlated. So that's also why we try to use these machine learning model to explore this correlation. So Huffman coding, again, you can achieve a fair performance, but not that good as these transformer-based or some deep learning-based method. So this table here shows the compression ratio, where we can also see that the deep learning-based or these transformer-based achieves a better performance, better compression ratio than the Huffman coding, the conventional method. So just now for all these previous slides, we talk about the lossless compression technique, but that's just for lossless compression. How we gonna use this compressor into the PDCCH. So this slide shows the architecture we need to embed these DCI compression into the PDCCH wireless system. And it's easy because we can simply just put the DCI compressor in front of before any channel encoder at the transmitter side. And then at the receiver side, we just need to do the DCI decompression after the channel decoding. And again, because it's lossless compression, so you wouldn't introduce any errors to the control bits. So you can easily just follow at the receiver side, you can easily just follow the encoding structure, lossless encoding structure, to lossless decompress these received DCI message. So some numerical results of the frame error rate, because this reliability, the better the reliability, the better that, I mean, the higher the compression ratio, the better of these decoding performance we expect to achieve for these PDCCH. And here again, we simulated the 5G NR PDCCH with polar encoder. And then based on some transformer-based lossless compression techniques, we can achieve better reliability for these PDCCH. It's simply because we have shorter length for this DCI message. We are able to use more number of redundant bits to protect these DCI payload. So from coding theory, you also know the lower the code rate, the better of these decoding performance we expect to see from this channel decoder. So this again proves that our proposed technique is useful, and it can greatly improve the reliability of PDCCH. So just now I showed some numerical results from a simulator. So here we also collected some Nokia DCI traces. So great thanks to our mobile network colleagues there. They provided some real life lab test Nokia DCI traces. And again, we can see that with machine learning techniques, we can greatly improve the compression ratio compared to the conventional method, like Huffman coding here, the baseline we use. So It also shows that even in the lab test data with some real-life DCI traces, we can achieve a better compression ratio by using a transformer architecture or any other deep learning approach. So one more slide about the scheduling scheme. As I mentioned just now, we have to put that into the standards, we need some signaling exchange between the user equipment and the GNOB. So simply, if we want to train a neural network predictor, these UE will need to coordinate with the GNOB. So the UE will need to let the GNOB knows when to start the training. And then once the training phase is done, then these GNOB will simply just share the transformer model in our case to the UE. Because one thing I want to highlight here, to achieve this lossless compression, that this deep learning model has to be aligned, has to be exactly the same for the UE and GNOB, because the probability distribution estimate has to be matched between this UE and GNOB. One last slide is about the future work. What we are working on now is this joint source and channel coding. Because as you may notice from previous slides, the compressed length is not constant from this deep learning based approach. There's a variance there because the deep learning approach doesn't guarantee the a fixed length from these lossless compressor. So one way to solve that is we can jointly combine these lossless compressor and the channel encoder into one neural encoder. In that case, we will guarantee that the encoded message is already the encoded message is considered by these neural encoder already. So it jointly combines the functions from the lossless compressor to the channel decoder. In that case, the encoded message will just be directly modulated and then transmitted through the PDCCH, that channel. So this is what we're working on now, and it will solve the problem of these variance of the compressed length from this deep learning approach. So some concluding remarks for this presentation today. I've shown that we propose this transformer-based lossless compression algorithm. It has achieved very good performance on the compression ratio compared to conventional method. And we have also shown that how to embed this DCI compressor into PDCCH that improve the reliability of PDCCH. So in the end, we are able to control more UEs by using less number of resources. And I've also shown some signaling scheme to indicate the idea of how to put this scheme into standards so that the UE and GNOB can exchange this information about when to update the model and how to share these trained model. And lastly, I've also shown one slide about what we have been working on here about the joint source and channel coding. That is promising, and we expect further performance gain on the reliability of PDCCH by this joint source and channel coding. So I think, yeah, these are all the slides I prepared for this presentation. Feel free to let me know if you have any questions or comments. So thank you.